In our previous lecture, we studied how to use matrix partitioning for manipulation of matrices. Today, in this lecture, we will utilize that concept to eliminate some of the buses or nodes in which there is no source or current source connected to them. So let us see how to use that technique. The standard equation in matrix form, admittance matrix form for the various nodes or the nodal equations is given by the current vector is equal to the admittance matrix into bus voltage matrix or the vector. Okay. Now, for example, if there is a power system, let us say it is having 3 buses, and 4th bus is, let us say, is the reference bus, and this we are given that a generator is connected and this bus is, let us say, connected like this. Similarly, in this bus a generator is connected through an impedance or the reactance, and this bus is also connected through some reactance or the transmission line. Now let us say this is bus number 1, this is bus number 2, and this is bus number 3. Now this generator can be converted into an equivalent current source. Like this, where let us say if it is VG1 and XG1, then this will be simply XG1 and this will be VG1 by XG1. If it is J, then J will come here and this will get connected to bus 1 like this. So you see that there will be some value of voltage here, which will be the bus voltage for the bus 1. This will be some voltage for the bus 2, and this will be having some voltage, let us say V at 3, or the bus voltage at bus 3. Now this source can also be converted into an equivalent current source. So the only bus remaining where there is no current source entering into it is given by bus number 3. So the admittance matrix or the nodal matrix, how we will write for this power system? We will say that the bus 1 current, bus 2 current, and bus 3 current is 0 entering into the bus. The source current is given by the admittance matrix for the power system and various bus voltages. Now in this lecture we will see how to eliminate a bus which is not having any current source entering into it. That is, we can eliminate this bus number 3 from this equation. However, you will see that this is possible only if when the current source entering into that bus is 0. There can be bus voltage, that is this element can be non-zero, but if this is 0, then this bus can be eliminated. This thing we should keep in mind. Okay, so you see that this voltage can have some value, but since the current entering, source current entering into this node is 0, so even if it is having any bus voltage, we can still eliminate this node and we can write the nodal equation like this: I1, I2. Here this admittance matrix is of 3 by 3 order. Here the new bus admittance matrix will be Y prime, let us say, and it will be of 2 by 2 order. V1, V2. Even though this V3 was not equal to 0, but in this current equation it does not appear here. Okay, but we should always remember, if it was not equal to 0, if it was having some value, let us say some x value, then we could not have eliminated this bus altogether. Okay, so we should keep this thing in mind. Now we will see how to utilize matrix partitioning for elimination of those buses which do not have any current source entering into them, and we will see that in the next slide. Let us say that we are given a power system which is having 3 buses and 4th is the reference bus, and the bus number 3 is not having any current source entering into it. Okay, so I will write the nodal equation as I1 I2 0 is equal to y11 y12 y13 y21 y22 y23 y31 y32 y33, and this will be the bus voltage vector V1 V2 V3. Now the first step is to write such that we can somehow group the non-zero current part into a separate matrix element, separate vector. Let us say like this, I1 I2, and I call it as a vector having IA. Okay, and this is separated like this. So I have partitioned this current vector into 2 parts, IA and IX, where IA is a 2 by 1 vector having I1 I2. Okay, so from our previous lecture we know that if R and R plus 1 row has a partitioning line in between them, then R and R plus 1 column will be having a partitioning line. So we will see that in this admittance matrix we will draw a partitioning line here. That is, if it is between row 2 and row 3, then it will come between column 2 and column 3. Now you should also note that in our case I have taken bus 3 as having current 0 entering into it. If there was some other bus, let us say I4 was also there and I4 was not having non-zero value, then we will have to modify the admittance matrix accordingly so that we can have the 0 element part in the last, that is the highest row part shall be having the 0 element. Here automatically it is the 3rd row, so it is the highest order element, y22 y23 y31 y32 y33 v1 v2 v3. Now let me draw another horizontal line like this. Okay, now this admittance matrix has been divided into 4 parts. This is part 1. Let us say it is K, and this is part 2, a 2 by 1 vector. Let us say it is L. Now for any passive bilateral network, which a power system usually is, we will see that Yij is equal to Yji. So Y13 is equal to Y31, Y23 is equal to Y32. So if it is L, then I can write it as L transpose. Okay. Now the last matrix, submatrix is M, although it is just a single element matrix. Okay. So I have partitioned the Y matrix into 4 submatrices K, L, L transpose, M. So writing it in this form, what I can write? IA, IX is equal to K, L, L transpose, M. And this is, let us say, VA and this is Vx. You should note that in this method we could have multiple zero values. Let us say if there was some bus 4 having zero value, then again we would have partitioned it like that, and this element will not be a single element part. It would have been some kind of matrix. So writing it further, we will see that this is VA and this is Vx with the given partition. Now you see, I can write from this equation that IA is equal to KVA plus LVX. Let us say this is equation number 1, and similarly IX can be written as L transpose VA plus MVX. This is equation number 2. Now I know that IX is a zero matrix because it is having only 0 elements. So I can write that 0 is equal to L transpose VA plus MVX, or minus L transpose VA is equal to MVX, or Vx can be simply written by pre-multiplying with M inverse, and I will get M inverse L transpose VA. So from this I have got this equation, Vx is equal to minus of M inverse L transpose VA. Now I will put this value in equation 1. What I will get? IA, you should note that this is a matrix equation. So all the time we should be careful about the order of the multiplication or the order in which we are writing various matrices. Okay, so IA is equal to K times VA, again various matrices, plus L into minus of M inverse L transpose VA, or it implies that IA can be written as K minus L M inverse L transpose into VA. I have taken VA common. So you see that now I have reduced a matrix which was having IA and IX into just IA is equal to K minus LM inverse L transpose VA. Let us say it is equation number 3. Now for our example which we have taken here, we will see that this equation is a very simple equation, and we will see it in the next slide. Now let us use this equation in our example. IA is simply I1, I2, and instead of Y this is Y prime, which is nothing but K Y11, Y12, Y21, Y22 minus L. What is L? L is nothing but y13, y23 into M inverse. Now M here is just a single element. So for a single element, what is the inverse? It is nothing but the reciprocal. Okay, so it will be simply divided by y33. And here comes L transpose. y31, y32. And this whole is multiplied by VA, which is nothing but V1, V2. So for our case, this matrix equation has become very easy. Okay, but you see that all the elements have got changed now. We will see how. On further simplifying, I will see that I1, I2 is equal to y11, y12, y21, y22. I will take 1 by y33 outside. What it will become? y13, y31 plus it will become a 2 by 2 matrix. Okay, because this is a 2 by 1 vector and it is 1 by 2 vector. So their multiplication will become a 2 by 2 matrix. y13, y32, y23, y31, y23, y32, v1, v2. This whole is multiplied by the bus matrix, bus voltage matrix. Okay, now you see that to get the final element, this is nothing but y prime, the new admittance matrix, the equivalent bus matrix when the zero element buses have been eliminated. Now if I want to write, let us say y prime as a matrix which is will be a 2 by 2 matrix, as let us say y11 prime, y12 prime, y21 prime, y22 prime, then the value of these elements can be written through this equation, and we will write that in the next slide. For example, we will write the value of y11 prime. So or let us say write a value of y12 prime. y12 prime is nothing but y12 minus 1 by y33 y13 y32. You can see that from, let us say this is equation number A. You can see that from equation number A, I have written this element y12 prime as y12 minus y13 y32 divided by y33. From this equation, let us say this is equation number B, I can make a generalization. What it is? It is that yij new, that is the new element, is nothing but yij old, which was y12 here, minus ynn, where n represents the order of the matrix. It was a 3 by 3 matrix, so n was equal to 3 here, into yin ynj. That is the element will be having from that row in which the old element was there, the first element and the last column. Similarly, again this element will be from the last row and the column same as the required element. So let us say this is formula C. Now this formula is a general formula which can be used to find all the elements of this new matrix. However, this formula will be required to be utilized for each and every element. Like here, I will have to utilize it 4 times. First for this, second for this, third time for this, and fourth time for this. So by utilizing this formula 4 times, I can write the new admittance matrix which was nothing but Y prime. And accordingly, the final nodal equation will become I1, I2 is equal to y11 prime, y12 prime, y21 prime, y22 prime into v1, v2. Okay, so here we have eliminated the bus number 3 which was not having any current source connected to it. Now you see, in this derivation we have derived 2 kinds of methods. The first method is to eliminate one by one. That is, I am eliminating one row each time. Okay. And other method was that I was eliminating all those rows which were having 0 elements, in which I had to write the value of M inverse. In our specific case, since I was just eliminating single row, so it was just a single element. But for those cases, if we were having, let us say, more than one row to be eliminated, then this element would have been a square matrix and we would have to determine the inverse of this matrix, which can be very tedious if we are not using any computer. So instead of directly writing the equation which was just nothing, let us say IA is equal to K minus LM inverse LT VA, where we will have to write M inverse, which will be again tedious, I will utilize most of the times this formula which is valid for one by one elimination of the 0 element rows. But using this formula, we should always keep in mind that the row which we are going to eliminate should be in the highest order. That is, we should always rearrange all the elements of the current vector, the admittance matrix and the bus voltage matrix such that the row which we are going to eliminate is having the highest order. Now let us say we were having a power system in which I1 would not be 0, I2 may not be 0, and I3 was 0 and I4 was not 0. Okay. And let us say it was having a admittance matrix Y11, Y12, Y13, Y14, Y21, Y22, Y23, Y24, Y31, Y32, Y33, Y34, Y41, Y42, Y43, Y44, and the bus voltage matrix as V1, V2, V3, V4. Then to use this formula, we would have to renumber all the rows and the columns such that this 0 comes here and I4 goes here. We will see how to renumber in the next slide because there is no space here. So let us say that I am given a power system which is having 4 buses, I1, I2, 0, I4, and the admittance matrix is y11, y12, y13, y14, y21, y22, y23, y24, y31, y32, y33, y34, y41, y42, y43, y44, and this is the bus voltage vector V1, V2, V3, V4. Now let us say we want to eliminate this row using the formula C which we derived in the previous slide. Now to proceed further, what I will do, I will renumber such that this row comes here and this comes here. So how will I do? We will see. I will write I1, I2, I4, 0. Now this is the crucial part. How I will write the admittance matrix. Y11, Y12, Y14. Instead of writing Y13, I will write Y14 first because I have renumbered 3 to 4 and 4 to 3. That is, I will replace 3 by 4 and 4 by 3. So it will come Y13. Again, Y21, Y22, 3 will be replaced by 4, Y24, and 4 will be replaced by 3, Y23. Y41, 3 is replaced by 4, Y42, Y44. This is again a crucial part. Y44 instead of Y33, and it will come out to be Y43. Now 4 will be replaced by 3, Y31, Y32, Y34, and this will come out to be Y33. You see, this is again a crucial element. So here students will usually do very many mistakes while renumbering. Okay, we should keep this thing in mind. And this will come out to be nothing, V1, V2, V4, 0. Now I can utilize the previous formula which we have derived for eliminating this row simply by writing Yij new is equal to Yij old minus Ynn. Now this Nn is this. I should have, instead of writing 4334, I should have renumbered all the items. Then it would have been easy to use this formula. And it will come out to be Yin into Ynj. Here n is 3 because instead of renumbering, I have kept the numbers same, 3 and 4. So in this way, I will find the value of each element using this formula. Here n is 3. Because I have not renumbered the elements, I have just changed their order. Okay. So in this way, I can find the new matrix, which will be, this matrix is a 4 by 4 matrix. The new matrix will be only a 3 by 3 matrix. And this row will be eliminated. And these will be new elements. So you see, in this way, we can eliminate all those buses which are not having any source connected to them, and this will help us to reduce the number of equations in our questions. So if you find that this lecture is helpful to you, then please share and subscribe my YouTube channel. Thank you.